4.1 is the fundamental counting principle, or just the counting principle that's here. Those of you who did the pre-calc 30 will be familiar with this already because it's a section, one of the last sections that we covered in the pre-calc 30 class. So what we're going to do with this one is determine what the fundamental counting principle is and then use it to solve problems. So the fundamental counting principle says if there are A ways to perform one task and B ways to perform another task, then there are A times B ways of performing both. So if you've got 6 ways of doing one thing and 7 ways of doing another, altogether there's 42 different ways of doing those activities. So example 1 says, selecting a strategy to solve a counting problem. So there's a few different ways that you can do this. We're going to kind of work from not necessarily the hardest, but the more time-consuming way, and then work our way up to the most time-efficient way of doing it. So it says Hannah plays on her school soccer team. The soccer uniform has 3 different sweaters, red, white, and black, and 3 different shorts, red, white, and black. How many different variations of the soccer uniform can the coaches choose from for each game? So to use a tree diagram, what you do is you would start with one of your items, so either the sweater or the shorts, and those will be your basic starting point. So, for uniforms then, if we start with our sweaters, and instead of writing red sweater, blue or black sweater, white sweater, I'm just going to put sweaters on the side here. So then you have red, white, or black. Then depending on which color you choose, then you can decide on what socks you want to wear with them. So with your red socks, you have a choice of red, white, or black. And I'm just going to go lazy way here and just use the letters. If you choose the white sweater, then you can wear red, white, or black socks. And if you chose, or if they chose the black sweater, they could choose red, white, or black socks to wear with that. So altogether then we have 1, 2, 3, 4, 5, 6, 7, 8, 9 possible uniform variations that they can choose from. So method 2 is using the fundamental counting principle. So the fundamental counting principle says if you have one type A and one type B, then your total choices are A times B. So number of uniform variations, we have 3 choices for our sweaters times 3 choices for our socks. So altogether, we have 9. So there are 9 different variations of the soccer uniform to choose from. So you can see where the tree diagram is good for a visual of what you can do. If you're just looking for the answer, the fundamental counting principle is just that much faster. So example 2, it says a bike lock opens with the correct 4-digit number. Each wheel rotates through the digits 0 to 9. How many different 3-digit codes are possible? Sorry, that should be 4-digit codes. So number of different codes. So how many choices do you have for the first digit? Well, you have from 0 to 9, so that means you have 10 choices. So that's for the first digit. Second digit, it doesn't say you can't repeat the choices, so that would mean you would have 10. For your third digit, then you would have 10 choices, and your fourth digit, you would have 10 choices. So 10 times 10 times 10 times 10 means that you have 10,000 different 4-digit codes that you could make for that combination. So this is where you see doing the fundamental counting principle saves you a lot of time. If you did that tree diagram, you'd be going on for pages and for quite a long time. So now it says, suppose each digit can be used only once in a code. How many different codes are possible when repetition is not allowed? So that means for your first digit, whichever way you start, if you start at the end or at the beginning, doesn't matter. But your first digit, then you've got that 0 to 9. So let's say for your first digit you chose a 3. Then that means for your second digit you're only left with 9 choices. So let's say it was a 5. That means for your third digit you have 8 choices. And for your fourth digit then you're left with 7 choices. So then your choices, when you multiply those all together, is 5,040 different 4-digit codes or combinations when you can't repeat digits. So you can see there's almost half of what you normally would have had. So it says the fundamental counting principle applies when tasks are related by the word and. Okay, so that's key. If you see the word and, if tasks are related by the word or. So when you have the word or in there, it says if the tasks are mutually exclusive, they involve 2 just disjoint sets. So that would mean that your number of choices, or depending on what the question is, the number of codes, if it was like this, would be A union B. So if they're mutually exclusive, then you'd have the number for A plus the number for B. So remember in Venn diagrams, if you drew a mutually exclusive one, that means they would be like this. This would be A and this would be B. They wouldn't have anything in common. There wouldn't be any overlap. So it says if the tasks are not mutually exclusive, then they involve 2 sets that are not disjoint. And we're going to call those sets C and D. So if they're not mutually exclusive, then that means they have an overlap. So they would be like this. This would be set C. This would be set D. And the overlap is what they have in common. And if you remember when we were doing this in the last chapter, if we are finding out the number of elements in there of C union D, we did the number in C plus the number, whoops, I put that in on the wrong side of the bracket, number of elements in D minus the number in C and D, right, that intersection point, because if you don't take that out, you're counting those members twice. So it says the principle of inclusion and exclusion must be used to avoid counting elements in the intersection of the 2 sets more than once. That's just what I said. Okay, so whenever there is an and in there, then you're going to use the fundamental counting principle and multiply. If there's an or in there, then you're going to be using the union. And depending if it's mutually exclusive, you're just going to add your 2 sets. If they're not mutually exclusive, then you're going to use that principle of inclusion and exclusion. Okay, so let's try a couple more examples. So solving some problems when the fundamental counting principle does not apply. So with a deck of cards, it says, standard deck of cards contains 52 cards as shown. Count the number of possibilities of drawing a single card and getting either a black face card or an ace. So black face card or an ace, aces aren't face cards, so they're not going to be, what's the word I'm looking for? They're not going to have any of that overlap. They won't have any elements in common. They'll be disjoint sets. So if we think of this as a Venn diagram, if we call our black face card our set A and our ace our set B, then in set A, our black face cards would be in clubs, and we'd have Jack, Queen, King. Whoops, that should be a queen. Whoops. Oh, I got to do my alignment. And then you'd have your spades, which would also be Jack, Queen, King. In your second set, your B, you'd have your ace of spades, ace of hearts, ace of clubs, and ace of diamonds. So if we take a look at that one then, the number of possibilities of drawing a single card and getting either a black face card or an ace. So remember, there's this ace here. Since they're mutually exclusive, we can do number in A union B, so that's just the number in A plus the number in B. There is no overlap in that one because you can't have a ace that's a face card, or ace that's a black face card, or ace that's a face card. So what do you have here? Your number in A, we have 1, 2, 3, 4, 5, 6. The number in set B, we have 4. So the possibility, there are 10 ways that you can draw a single card and get either a black card or an ace. So what about a red card or a 10? So again, this is using that or. So when we set up our, we're going to use C union D. But when we think about our red card or a 10, these are all of our red cards here, right? This whole group here. And our 10s are here. So you can see between our two groups, if I do it like this, we have an overlap. So they're not mutually exclusive. So what that would look like if you did a Venn diagram, if C is our red card and D is our 10, so our C, we would have, let's do our overlap. So in here you would have 10 of hearts, 10 of diamonds. On our C side then, there was 26 red cards, so then that would mean we'd have the 24 red. Whoops, 24 red. And then for the 10s, there would be the other 2 that are red, so that would be the 10 of clubs and 10 of spades. So if we set this up, we know that because they're not mutually exclusive, we're going to do the elements of each minus the elements that they have. Whoops, that should be an intersect. Minus the elements that they have in common. So number in C was 24. Number in set D was 2. And the number in both of them, there were 2. Oops, I put the wrong, I need to put, this should be 26 plus 4 minus 2. So it should be 28. I was doing it without including those numbers in there. So there are 28 ways to draw a single card and get either a red or a face card. Okay, so in summary here, so fundamental counting principle, you're going to multiply when your tasks are related by the word and. Fundamental counting principle states if one task can be formed in A ways and the other task can be formed in B ways, then both tasks are formed in A times B ways. So what you need to know then, the fundamental counting principle can be extended to more than 2 tasks. If one task can be formed in A ways, another task in B ways, another task in C ways, and you can go on forever, then it's just multiplying those ways together. So A times B times C, all the way down to whatever letter you have, or whatever value you have. The fundamental counting principle does not apply when tasks are related by the word or. So in this case of an or situation, you either use the mutually exclusive when your sets are disjoint, and then you're just counting up the number of elements in each set and adding them up. And if they are not mutually exclusive, so the sets have some overlap or some elements in common, then you're going to use that number of elements in both added together minus the number of elements that they have in common. So outcomes tables, organized lists, and tree diagrams can also be used to solve counting problems. They have the added benefit of displaying all the possible outcomes, which can be useful in some problem situations. However, these strategies become difficult when there are many tasks involved and or large possibilities for each task. So as we said at the beginning, when it's a nice simple thing, the outcomes table like we did for proving statements as being conditional or conditional statements by conditional, inverse, converse, and so on, you can use an outcome table like that, or you can use the tree diagrams or some kind of a list that you can organize it in. They work well, they're a nice visual, but it's only good when you're working with small values. As soon as you get into more than 3 things, it gets very cumbersome and time consuming. So that's all. There are your questions to work on, 4 to 12 and 14 and 16.